Hi there and welcome to our linear algebra channel where we do everything linear algebra. In our first lesson today, we want to solve a system of simultaneous equations, which I put on the board there. It says x plus y plus z is equal to 2, 2y plus z is equal to 0, and minus x plus y minus z is equal to minus 4. Of course, there are various methods of solving such a system of equation, but the one that we want to discuss today is a method that involves matrices. So first of all, let's write our system over here and see where we go from there. So it's x plus y plus z is equal to 0. That's the first equation. The second equation says 2y plus z is equal to 0. Oh, sorry, I'm copying it wrong. The first one is 2 there. I beg your pardon. So that's 2 there. And the second one, the third one, sorry, it's minus x plus y minus z is equal to minus 4. Okay, so the first thing that we want to do with a system like this is to change it into a form that is into a matrix equation rather. So we wanted to write it in the form Ax is equal to B, where x and b are vectors and A is a matrix consisting of the coefficients of x, y, z in all these equations. For instance, in row 1 of A, the elements are 1, 1, 1. In row 2, it's 0 because there's no x here, so it's 0, 2, 1. And in row 3, it will be minus 1, 1, minus 1. Our vector x is the vector of variables, so x is equal to the vector x. That's why I put a line underneath them. These are vectors. It's x, y, z. So it's a vector of variables. And vector b is the vector 2, 0, minus 4. 2, 0, minus 4. The vector on the other side of the equal sign. So now we want to write it in this form. So let's do that and see what happens. So our A, remember we say A is our matrix of coefficients. So 1, 1, 1 for row 1 of A, and 0, 2, 1 for row 2 of A, and minus 1, 1, minus 1. That is matrix A. And remember we said x, of course, is the vector of variables, which is x, y, z. And our B is the vector 2, 0, minus 4. So our new system becomes 1, 1, 1, 0, minus 0, 2, 1, minus 1, 1, minus 1, representing matrix A. Now here we have vector x, z here, sorry, our z there, and of course our B, 2, 0, minus 4. Now we have changed this system into a matrix equation. We can call this step number 1. Find a different pen. So this would be our step number 1. Okay. Step number 2, we want to construct a new matrix which consists of the elements of A with the elements of B together. That matrix is called the augmented matrix, and it's represented as A stroke B. Okay, it's a new matrix which consists of all the elements of A, which is 1, 1, 1, 0, 2, 1, minus 1, 1, minus 1, with the elements of B placed in juxtaposition, if you like. So that will be 2, 0, minus 4. This is now a new matrix. Notice A is a 3 by 3 matrix, and A, B, the augmented matrix, is a 3 by 4 matrix. 3 rows and 4 columns. 1, 2, 3, 4. So again, let's remember it's called the augmented augmented matrix. Let's summarize our steps so far. This was, of course, we can call this one step 2. So in step 1, we had to convert this system into that system where A is the matrix of coefficients, X is the vector of variables, B is the vector 2, 0, minus 4. That was step 1 there. Step number 2, we constructed an augmented matrix A stroke B, which is consisting of all the elements of A with the elements of B attached to them. It's a new matrix, different size to matrix A. It's called the augmented matrix. Now, the next step is critical. Critical not because it's difficult. I don't mean that by saying it's difficult, but what it means is this is where the real work began. The real work of getting to the solution begins. So, what is that real work? I'll get rid of, I will need my augmented matrix, but everybody else can go. So, I will put it up there, but before I do that, I will just leave it here so I can copy it once the board is clear. Okay, so this, we have it over there, so we don't need all this. So, okay, so first of all, let's copy our augmented matrix here. It's 1, 1, 1, 2, 0, 2, 1, 0, minus 1, 1 minus 1, minus 4. This has to be understood from the perspective of it's just capturing all all this information here and putting it in one box, because this part of the augmented matrix is representing matrix A, and it's the matrix of coefficients. So it still says x plus y plus z, and here it's equal to 2. In the second row, it just says there's no x, then 2y plus z is equal to 0. In the third row, it's saying minus x plus y minus z is equal to minus 4, just as it is. So this is now capturing all the information and putting it in one box. Now, we are going to carry out some operations on this matrix. And whatever we do to matrix A, because listen, A and B are attached together, whatever we do to A, it is also being done to B. So that by the time we get to a certain stage, we can still read off our equations just as it is in this form. Okay? But before we begin these algorithms, if you like, this series of operations on the matrix, we need to take care of certain rules. Rule number 1, or things that we are permitted to do, we are allowed to exchange rows. I can take this row, put it here, take this one, put it there. Or this one, put it here, this one, put it there. So we can exchange rows. Rule number 2, we can multiply any row by a non-zero constant. You can multiply the whole of row 1 by 16, the system remains the same. You can multiply the row number 3 by 75, system doesn't change. That's rule number 2. Rule number 3, we are allowed to add a multiple of one row to another row. For example, we can multiply row 3 by 5 and add the result to row 2. System doesn't change. So with those rules in mind, let's proceed. Okay, now as we proceed, our aim is to have a leading 1 in each row if it is possible. Okay, looking at our matrix here, row number 1, there is a 1 there. If there was a 2, we would have had to multiply row 1 by half so that this becomes a leading 1. But lucky enough, we already have a 1 here, so we're not going to do nothing about it. Sorry about my English. In the next row, we want our leading 1 here, if it is possible. Well, we don't have a 1 here, so we will have to play around with things until we have a 1 here. The same applies to this row here. we have to get a way of making sure here we have a leading one. We want our leading ones to be, the first one will be here, the second one will be there for this particular matrix, and the third one will be there. Okay? And once we have a leading one, the other thing that we want to achieve is that everything below it must be 0. All right, let's see. Here is a leading one in row 1. There is nothing here, so we are lucky. We're not going to do anything. But down here, there is a -1, so we need to get rid of it so that there is absolutely nothing below the leading one here. So what do? We are going to add 1 times row 1 onto row 2, which means we take our row 1 as it is, it's fine. Then our row 2, remember there is nothing here, so we don't need to do anything. There's a 0 there. Now, to get rid of this, we must add 1 times row 1 to row 3. So 1 plus -1 gives us a 0. 1 plus 1 gives us a 2. 1 plus -1 gives us a 0. 2 plus a -4 gives us a -2. Okay? So, with the leading one in the first row, we are done. Now we can almost close off row 1 and pretend we are now dealing with just this part of the matrix. Okay? Let me fence it red just to show you what I'm talking about. So we can mentally close off row 1, but I just want to illustrate what we are doing. So here now, we need a leading one here. Either we can divide this by 2 so that we have a 1, but here we are going to have a half, which is not a very nice thing. But the way I see it, we can first of all divide this by 2, so we have a 1 here. And because the rules allow us to exchange rows, we can then take this, put it there, this one, put it down there. Let's do that. First of all, let's divide row 3 by 2. So we will have, remember now row 1 is out of the picture for the moment. So here we are. Notice I'm not putting equal signs because this matrix and that matrix are not the same. So I'm just putting this little thing there to show the direction in which I'm proceeding. So here is our 1 there, 1, 1, 1, 1, 2. And we write our row 2 as it is. We'll get to it in a minute. But we said we have to divide row 3 by 2. So that becomes 1, 1 here, 0 there, -1. Remember, we are allowed to divide or multiply by a constant as long as it is a non-zero constant. So, right, we have a 1 here. What can we do? Change this, put it there. Now we have a leading one there. Let's do that. Exchange row 3 with row 2. Come over here. We write our 1, 1, 1, 2. Now we are putting row 3 there. It becomes 1, 0, -1. Then row 2 comes down here. It's 2, 1, 0. Okay, fine. We do have a leading one now in row 2, but we don't want to see anything below it. We have to get rid of these 2 now. What do? We can multiply row 2 by -1 and add it to row 3. So let's do that. Again, I'm going to write my row 1 as it is. 2, 0, 1, 0, -1. And now I'm going to add -2 times row 2 to row 3. So -2 plus 2 gives me 0 here. 0, it just remains 1 here. -2 times -1 is 2 plus 0, that gives me 2. Okay, now it looks pretty good because I now have a leading one in each row. A leading one there, a leading one there, a leading one there. Our next assignment is to get rid of everything above the leading ones. Here, there is nothing, of course. Here, there's this one here. We've got to get rid of it. Here, there's that one there. So first, we take the third row. We need to get rid of everything above the leading one here. So what do? We simply subtract, or let's put it this way, we add minus 1 times row 3 to row 1. Let's do that. So it becomes here, of course here it remains a 1, here it's 0, it remains a 1, here it's minus 1 plus 1, which gives me a 0. Here it's minus 2 plus 2 there, it gives me a 0. Now here is my row 2, 1, 0, minus 1, 0, 1, 0, 0, 1, 2. That's the new matrix. Okay, now where do we go? We need to get rid of this guy as well. We are done with this guy. Now we need to settle this guy. We need to get rid of that. So we simply add minus 1 times row 2 onto row 3. So let's do that. It then becomes here, it's 1, but minus 1 plus 1 gives me a 0. 0, that gives me a 0. Minus 1 times minus 1 is equal to 1, plus 0, that gives me a 0. Then row 2 comes here, it's 1, 0, minus 1, 0, 0, 1, 2. This guy is sorted, this guy is sorted, we've got a leading one everywhere, we are done. But what does this mean? Remember, again, this matrix here, let me come over here so you can see. This matrix here represents a matrix, is a matrix of coefficients. It's still representing those coefficients. So here, y is gone, z is gone. We are just left with an x. And x here, this is vector b. Remember what we were doing to matrix A, we were also doing to matrix B. A was reduced to this, B was reduced to that. There's no cheating that was involved. So therefore, what it reads now is x is equal to 1. Originally, it was x plus y plus z is equal to 2. We reduced everything, played around until we are left with x is equal to 1, y is equal to minus 1, z is equal to 2. This form of the matrix, first of all, this form of the matrix where we now have a leading one in each row, or any non-zero row, because sometimes you can end up with a row of zeros. Well, we're not worried about that. But as long as there is a leading one in every non-zero row, which we have in this case, such a matrix is said to be in row echelon, I don't know how to pronounce that, echelon form. For this matrix here is in row echelon form. We proceeded from this form here all the way until we got here. When we get here, the matrix is now in reduced row echelon form. I'm not so sure if my red ink is clear there, but this is reduced row echelon form. That's the form where you can now read your values of x, y, z. And this whole operation that we performed on our augmented matrix is called the Gauss-Jordan Ellimination. So it's the Gauss. It's named after Gauss, the famous mathematician or whatever. Gauss, Jordan is also another guy. Jordan elimination. Elimination. Okay, so probably let's just slowly summarize what we did. First of all, we had our augmented matrix. Then our first target was to obtain leading ones in all the non-zero columns. In every column that was a non-zero column, we needed to have a leading one as in this one. So we do all our elimination or our operation until we get a leading one in a row. But the other thing is that we need to eliminate everything that is below the leading ones until we get to the row echelon form. So that's what we were doing all the way until we got here to the row echelon form. From the row echelon form, we then start to eliminate everything above the leading ones until we get here and we obtain the reduced row echelon form of the matrix. There is nothing that has been changed because what we were doing here, we were doing to matrix A. And what we can do now is simply to read off the values of X and Y. It was a rather long process, but you always get there, provided you follow the steps. And of course, as you can see, it is the arithmetic really, which is rather heavy. The steps are easy to follow as long as you remember the rules, but it's the arithmetic that you have to be